Welcome back. So now we are in module 1.4 on control hijacking. So now we'll be focusing on defense against control hijacking. So far we have been seeing how control hijacking happens and how various vulnerabilities are exploited to hijack control of a running program. Now there are two ways to do control hijacking defense. So one is at the platform level. So the platform level in the sense that the operating system, even the hardware, or the runtime environment has certain defenses against the control hijacking. But the other one would be runtime defenses. During the execution of the program, various checks and balances can be done in order to make sure that control hijacking is not happening. So in this module, we'll talk about platform defenses. So let's see what we can do. So first of all, if we fix the vulnerabilities or the bugs in the software that lead to this kind of exploits, then of course we can prevent it. So one common way is to do software auditing. So in large companies, every time a software is implemented, the whole team sits together and do auditing of the software, sometimes manual auditing, where they actually go through each other's code and try to flag the problems that they might find. The other is to use automated tools, like so for example Coverity. There is also tools like Grammatic, Code Scanner, or Code Sonar. So these are the tools that can be used to find these vulnerabilities. Now most of the time these tools are not foolproof. They cannot find 100% vulnerabilities of this kind. The reason is discovering these vulnerabilities is equivalent to finding reachability of a particular part of the program, and we know that for arbitrary programs reachability is undecidable. So therefore all the tools, they actually try to do their very best, but they have to do some kind of a abstraction, and that lead to false positives. And when a tool produces too many false positives, the programmers get frustrated and then they stop using the tool. So the main focus of many of these tool vendors is to reduce the number of false positives and increasing the number of real bugs that they can find. But the other issue about these tools is that these tools are quite expensive, and sometimes it's not affordable for small software projects. And another is that many of these tools are often embargoed by by the country in which this these tools are being developed for export. So you cannot necessarily get them here in India, for example. The other thing that Microsoft has done, so Visual Studio now has a advanced version in which they have a thing called Analyze. So you can actually do analysis on the code that you write if you are subscribing to that advanced version of Visual Studio, and that also does something similar, basically static analysis of the code to figure out whether an input is going into a vulnerable function without being sanitized. Of course, the programming language experts will tell you that don't write in C and Perl and Python and all these unsafe languages. Use type-safe languages like Java and ML or Haskell. But that really is not a solution, because most of the code base we have and most coders today are actually still using C, C++, and all these languages. Plus, it's not true that type-safe language means that there is no vulnerability, depending on the type system they have, and there is a lot of research going on the type system that can actually check for this kind of vulnerability during type checking. And the second approach is to accept the fact that there will be overflow, there will be program vulnerabilities, and therefore the approach there is to prevent the code execution beyond the point where overflow happens or control hijacking happens. So you have to detect that control hijacking is happening, and then accordingly stop the program or do something, or do some recovery action. The other one is that you do a runtime check. So you add runtime code, and when overflow happens, this runtime code will check that overflow has happened. Then you halt the program, and this runtime code insertion into your code has to happen automatically, because otherwise, it's very difficult to go at every point of this program and start add runtime code. Because if it was possible, or if it was easy, then the programmers would have done it in the first place by writing very, very defensive code. So the first approach to platform defense was called the DEP, or data execution protection. So in the examples that we showed in buffer overflow, you saw that in many cases we did the buffer overflow, and then we put the program P into the stack itself, and then we pointed the return address to that location or an op slide before that location. So in that case, what is happening is that the reason why this malicious code could execute is because it is being picked up from its location in the stack itself and being executed. So now if you say that if you ensure that stack is not executable, so anything that resides on the stack has to be data. Anything that's not in the code part of your memory is not to be executed, and this is called non-executable data, or data execution prevention, or DEP. So there is a specific bit that was introduced by in Ethelon 64 as well as in Intel P4 Prescott onwards. So this is a processor architecture level solution, and this NX bit is there in every page table entry. So any page that has the memory for this stack, it will not be executable, and NX bit is set to be 1 if it is not to be executed. And then we find that Linux, OpenBSD, Windows since XP Service Pack 2, and even the environment provided by Visual Studio, they actually provide a compile time flag to say that it should be DEP compatible, so that you cannot succeed attacking the program by putting the code in the overflow string itself. Now this doesn't always work. The reason why it doesn't always work is sometimes, for example, the heap cannot be made non-executable. In case of systems that use just-in-time compilers, or JITs, so they need the code to be generated as the program executes, and therefore the heap has to be executable. So you cannot do that. Also, there is something called return-oriented programming, and return-oriented programming, will look into that, does not require the code to be in the stack or in the heap. It actually only need the addresses to the code to be on the stack on the heap, and that, after that it's in some place where in the memory that is not subject to data execution prevention. So in Windows you can actually turn on DEP. So this shows where and how it is done, and then so when you try to execute a program and it is actually trying to execute code that is part of the non-executable part of the memory, then you will get some message like this. Now the attackers are always finding ways around the defense mechanisms. So return-oriented programming is something that is there to circumvent this DEP defense. So in this, what happens is that instead of earlier examples, we had this program P in the stack itself by overwriting the content of the stack. What you would do here is that in this you have the code actually as already part of the library. So you basically take various functions that are already part of your own code or in the dynamically linked library or statically linked library, and you know the location of that code in the memory, and for that you have to do some experiments with the particular architecture and operating system and so on, and you figure that out, and then you basically do something like this. So you take the return address, override the return address, not to point to something else in the stack, but to the part of the memory where this library functions are. So in this case, for example, exec. So you put the address of exec here, and then exec takes the arguments, and in this case the argument would be a shell, if you want to inject a shell, for example. So this is the shell program, and so in the arguments you overwrite with the payload or whatever program you want to execute by exec, and in this case it's the shell, and therefore you will be executing a shell. So whoever is doing this will get a shell, and if the original program is running as a root user, then you will get a root shell. Now in response to that return oriented programming, what you do is you do a randomization of the memory layout, and this is called ASLR, or address space layout randomization. So what you do, instead of putting the shared libraries to a fixed set of locations, you actually randomize it, and for every instance of the process it will be at different location. So therefore the attacker cannot directly know that where exec function is placed, and therefore cannot use this technique. And so Windows 7, for example, allows 8 bits of randomness for DLLs, and so there are 256 different choices. For Windows 8, the number of bits of randomness is more. The reason is that for 256 choices, it's not that difficult to figure it out in a brute force way. With 24, it's a bit harder. You can also do syscall randomization. So system calls have IDs. So actually, in this previous example, normally what you would see is that in the return address, instead of writing exec, you will actually name the syscall number. So if you can do a syscall randomization, then the attacker cannot imagine what would be the syscall number for exec for this particular instance. There is also instruction set randomization that is done. Now instruction set randomization is actually a high overhead technique, because you would be XORing the instruction set with random bits, and then when you are actually going to execute, you have to unrandomize it, and therefore normally, unless the system is extremely critical, you would not want to use some such high overhead technique. So here is an example of ASLR from a real system. So we have booted a system twice to load libraries, and you can see that the same sequence of libraries are actually at 2 different locations for 2 different boots. So this shows that the ASLR is at work. So and you can actually randomize everything, stack and heap and shared libraries and base image. You can also put the base address of the stack and the heap and so on in the memory layout also in a randomized way. So although you don't have in a 32-bit address space that the scope of randomization is limited, but for 64-bit address space, the scope of randomization of the base address of stack or heap are actually quite large. So Windows 8 onwards, they force ASLR, and all loaded modules use ASLR. Earlier it used to be a choice by the person. So that basically finishes the our discussion on platform-based defense. Of course, this is not everything. There are lots of different ways and lot of more details about ASLR or these randomization techniques, instruction set randomization. Even for the return-oriented programming, there are more techniques to defeat ASLR and so on, and there will be some material posted on the website to actually get deeper into this. But as far as this basic knowledge is concerned, this is what you need to know in order to do your projects, for example. So, so now next we'll go into the runtime defenses in the next module, and we'll see other than platform defenses what we can do at runtime to defend against control hijacking.